In this lecture, we will cover the basics of optimization algorithms, the framework in which the algorithms operate. So these are the three things: the algorithms, their convergence, and algorithmic strategies. So algorithm, to begin with, is a process or set of rules for a calculation or a problem solving operation. This is the dictionary meaning. Okay? Quite often, the algorithms that we talk about will be iterative, and typically an iterative algorithm would start from an initial solution x0, which may be quite wrong, doesn't matter. Okay? And the algorithm will consist of a systematic process to generate a sequence of solutions. From x0, it will generate x1, from that x2, and so on. And as long as you let it run, it will go on generating one solution after another. So that is what an iterative algorithm is. Let us take an example. So you see this recursive definition of xk plus 1. So to calculate the next x, you need a previous one. So start from somewhere. Okay. So whatever you feel is possibly close to a solution, or if you have no such feeling, start from anywhere. Now, so s is a given positive number for which you are running this. Okay. So suppose we take s equal to 9. So starting from x0 also say 9 only we give. We don't know anything. The generated sequence happens to be after 9 it gives 5, then 3.4, then this, and you can see where it is going. So as it happens, it goes to 3. If we start from some other number, 0.5, then next is this, next is this, next is this. Incidentally, this also will eventually go to 3. There is good reason behind it. It's not incidental. As you check further, you would notice that the sequence always converges to square root of s. At whatever positive x naught you start. If you start from a negative x naught, then it will converge to minus root over s. This is in fact the age-old Babylonian square root algorithm. So it was designed to get square roots. Okay. So this is an example of an iterative algorithm which converges. And that issue of convergence is what we discuss next. If the limit of the iterates as number of iterations goes indefinitely high is something, to begin with, if that limit exists, and then if that limit is x star, then we say that the sequence of xk converges to that value x star. Okay, so this is the definition. Now, how do we evaluate and compare algorithms? First of all, if one converges, another does not, then we know that the one that converges to the required solution, that is better. But if we have several algorithms, all of them converge in this sense, then how do we compare? Then we will compare on several bases. So whether they are useful, whether they are good or better than another. So to work out these qualitative notions, we work with some quantitative concrete ideas. Let us see what are those. Two distinct and different notions of algorithms, of convergence of an algorithm are there. So one notion talks about effectiveness and the other about efficiency. So the issue about effectiveness started from an arbitrary point, okay? We don't have any sense of what can be the final solution. Started from an arbitrary point, x naught, do iterations necessarily improve on it? That is, are the next iterates going to be any better than the previous ones? That is, does xk approach x star, which is a solution of the problem? So if it does, then you say that the algorithm has global convergence. That means from anywhere, if it approaches the final solution slowly, no problem. But if it does approach, if it comes closer, then you say that it has global convergence because it could start from anywhere and come there. Okay. So answer to this question, does an algorithm have global convergence, can be in yes, no. Okay. So the second question is about efficiency. Started close to x star, that means this issue has been sort of settled or avoided. Okay. Started close to x star, at what speed does the algorithm approach it? Okay. So this question is known as local convergence. And the answer to that cannot be in yes, no. It has to be in numbers. So some number will signify fast convergence, some number will signify slow convergence, and so on. Okay. So these are the global convergence and local convergence are not two different answers to the same question. They are answers to two different questions. How effective is it and how efficient it is? And make note that the word global here in this context is talking about the location of the initial point, not the x star. For example, we are talking about approaching a solution of the problem, not the best solution. There may be several solutions of the problem, several optima for that matter, several minima, and one may be better than the other, but that is not being talked about here. We are not talking about global minimum. We are talking about a minimum. If we are talking about minimum. Okay. The word global here is not about global minima, but arbitrary location globally of the starting point. Okay. This is one mistake which many people somehow make out of prejudice and maintain it. So you try to avoid that prejudice. So the first question, global convergence. Started from anywhere in the domain, does the sequence approach an optimum x star? Optimum in the context of optimization problem. For a minimization problem, if you can show that the next iterate is better than the previous one, that is function value is less in the next at the next point, for every iteration, if you can show this, then it is enough. In fact, it is more than enough. You may not win in every deal in your life. Okay. So you say that my life is going in a better direction if out of quite a few deals that you play, if you win enough to make an improvement over a period of time, and if that kind of periods of time keep on coming, then you say that your life is going fine. Okay, going well, going good. So every deal you don't need to win. Okay. So this, if you can show this, this is not just enough, it is more than enough. Okay. The bare necessity for global convergence is that the sequence x1, x2, x3, x4, etc. must have a subsequence, something like x3, x7, x15, x28, x41, which has that continuously decreasing property. Okay. So I1, Y2, I1, I2, I3, I4, etc. are increasing numbers, and the corresponding iterates happen to be better, 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 and so on. That is good enough. Okay. In between, even if you have lost a few deals, it doesn't matter. So it means some upward steps will not be an issue as long as there is a guarantee of assured reduction over a finite number of steps. So in every bunch of a finite number of steps, that finite number also may change. It may be 4 steps and then 5 steps and then 19 steps, then 3 steps, then 4 steps, whatever. But if you can show something like that, this thing, then that is good enough. Okay. So let us consider this example. Consider an algorithm xk is kk. Okay, x1 is k and x2 is k. So that is xk. Kth iterate for vector x is kk. Make note that it is not an iterative algorithm, because in order to find out 17th iterate, you don't have to go from 1 to 16. Okay. To minimize this, suppose according to this algorithm, you proceed. Whatever. So if you remove this exponential term, okay, then if you consider here fx as r and this x2 as theta, then that r theta actually is the elliptic trajectory of a typical planet or comet. Okay, m is the eccentricity of that ellipse. So if you remove this exponential term, okay, so removing that exponential term, this is actually an elliptic trajectory with eccentricity m with x2 equal to theta around the focus r equal to theta, where the sun is supposed to be. Now fx, what is given here is then say r prime, and that is that r on the ellipse into this exponential term with a negative sign. That means this is the trajectory, this is the elliptic trajectory, okay, and rather than going along that ellipse, the object is all the time coming closer to the sun by this factor. Okay, so in an elliptic trajectory, the body will continue a cycle and come back to here with an exponential decrease of r. It will go in a spiral trajectory and actually converge to the focus, right? So this algorithm, cooked up algorithm, does converge to the focus, okay, but at every step this r prime does not decrease. You see, even in that spiral trajectory from theta equal to 1, that is k equal to 1, k is same as x1 and x2 and theta also. So theta as 1 radian, it's here, and the distance is this little. K equal to 2, it will be somewhere here, 2 radians. K equal to 3, it will be somewhere at this point near pi. Actually, it is increasing. So from k equal to 1 to 2 to 3, r prime is actually increasing. But there is a guarantee because of this expression that after a few such steps, it will come close. Okay. So it is globally convergent, though at every step there is no improvement. Okay. So for global convergence, only that much is required. But if you can show in addition that at every step there is a reduction, that's even better. As we said, more than enough. Okay. So most algorithms satisfy that, but satisfying this kind of a situation, this kind of a condition, which is the bare minimum, is also good enough. Some algorithms fall in that category, which are good algorithms for that matter. The second question was about local convergence. As the sequence xk converges to x star, at what rate does the difference or error decrease? Error is supposed to decrease to 0 if the iterates converge to x star, but at what rate they decrease? So in a concrete manner, you ask a question which one should understand, that for what p, this ratio, error at the next iterate divided by error in the previous iterate to the power p, is finite. So if you did not give this p, then for particularly fast algorithms, if the error in the next step becomes incomparably smaller than the result in the previous step, then it would be infinitesimal, okay, close to 0. On the other hand, if it were not so, if this were higher, okay, then without this p thing, it might have gone to infinity, which is very disastrous for that matter. So you ask for a value of p for which this ratio is finite, and then you say if p is 1, then it is a linear rate of convergence. That is, convergence is reasonable. If p is equal to 2, then you say quadratic rate of convergence. That is, it is fast. If p is in between somewhere, then you say it is better than linear, but not so good like quadratic. Then you call it superlinear. Okay. And based on the way the algorithm operates, in many cases you can establish this number. And in some others, you establish it statistically. In the sense that initial iterations operate like this, later iterations operate like this. So overall, it is this number 1.34 or 1.41, whatever. Okay. Then after you have found that p, whatever would make this finite, if you insert that p, then you get beta. Okay. And that also may depend on k. Then as k tends to infinity, what is the limit of that beta? Okay. After putting the value of p. That limit is known as the convergence ratio, which from the beginning it was. Okay. And if you are comparing two different algorithms, one having one rate of convergence, the other having another rate of convergence, then that is easy. But if you are comparing two algorithms having the same rate of convergence, then which is better, which is worse for local convergence, for speed of convergence, you compare this convergence ratio. The one having convergence ratios less will be a better algorithm, because that means that with a given initial error, the later iterate will show less error in that case. Now we revisit the first example. Okay, so this algorithm, this Babylonian square root algorithm, okay, for positive s. First question: does this algorithm converge? To which value? First round, through numerical experiments, we found that it converges always, okay, to root s. But I have not shown you that exhaustively, but you can see. Okay. Now, does the algorithm converge? And if so, then to which value? So to answer this, you say that if it converges to say x star, then putting x star here, you would get the same x star here. That means x star is a fixed point of the algorithm. So x star is equal to this. When you simplify this, you get x star square is s. Okay. Simply, you take 2 on this side. From there, you remove 1 x star. So what x star remains here is s by x star. Take this x star on the other side. X star square is s. This is why it converges to root over s. Now, we are interested to find out the rate of convergence. That is a little rigorous. So the error is xk minus x star, which is xk minus root over s. So put that. Okay. So ek plus 1 would be this, xk plus 1 minus root s, and ek will be this. And that to the power p from the definition is there. Now, in place of x star, you insert this expression. And then try to simplify it. As you simplify it, mod xk you bring here. This 2 also you bring here. So inside what remains? Xk square plus s minus twice xk into this. Okay, you are just simplifying it. And this is a complete square. So write that xk minus root s whole square. And now you see that if you had p equal to 2, then this would and this would completely cancel and you would get something finite. That tells you that the rate of convergence of this is p equal to 2. If you put p less than 2 here, then you will find that it is infinitesimal. Okay, because started close enough, this thing is small enough, and a small number, and above you have that small number square, which is even smaller, that would make it infinitesimal. Okay, so for p equal to 2, beta is finite. Then the next question is, what is the convergence ratio? So you put beta equal to 2 there, and then you get only this much. Okay. So you get only this much, and its limit as k tends to infinity, we have already seen that it converges to root s, and that is why you are getting this. Okay. So this is the convergence ratio. At this ratio, it comes down. Take another example. Say xk equal to 3 to the power minus k square. Again, this is not an iterative strategy, iterative algorithm. Okay. So ask the same questions. What is its fixed point? So x star equal to 0 is its fixed point that you can see. You put k equal to 10,000 and then you will find 0, almost 0. So, and here the algorithm converges. You can find out beta. So put 3 to the power this thing in k plus 1 terms, and here it is this to the power p. Now this k plus 1 whole square, you open it. So you get 3 to the power minus k square, minus 2k, and minus 1. Okay. The three things split in three parts we have kept. Okay. Now this part we have kept here because that matches exactly with this. We are interested in cancelling. So you find that in this case, p equal to 1 would make this cancel. Okay. So it's an algorithm with linear speed of convergence, p equal to 1. And then beta, finite beta will be this. And further, for convergence ratio, you will take its limit as k tends to infinity. And then you find that it is 0. And this kind of situation where officially the rate of convergence is superlinear, rate of convergence is linear because p turns out to be 1, but when you try to find out that ratio by taking this limit, the ratio turns out to be 0, then you say it is linear but very good kind of linear, and that is superlinear. So in such a situation, the convergence rate is said to be not just linear but superlinear. Okay? Take one more example of this class. Say this is an algorithm. This is again an iterative algorithm. Okay. So given a starting x0, you put that here. What you get is x1. Put that here. What you get is x2, and so on. So try this, and we should start asking the same questions. There is a fixed point. Okay, a point where it is supposed to converge, and that you get by putting x star here as well as here. And then as you solve, you get that value to be 0. So to 0, it is supposed to converge if it does converge. Now, the bad part is that the algorithm may or may not converge to this point, okay, depending upon the initial value. And that is why this is an example of an algorithm which is not globally convergent. Whether it will converge to its fixed point or not, that will depend upon the initial starting point. Started anywhere, you are unable to make the claim that it will converge. So this algorithm does not have global convergence. You can try it from two disparate numbers, and most dramatic case I will show you. Examine two sequences generated by this recursion. Started from 1.3917, it gives this, then after quite a few more steps, this, and then this. You can see that it is going to 0. It does go to 0. That is 1.3917. Now started from 1.3918, it gives this, then after a few more iterations, give this, then this, it is going away. Okay, as far from 0 as it can. So, and it will go out. Okay, so I leave it as exercise for you to figure out why this happens and why it happens around this. Okay, with so little difference. So there is a bifurcation there. Okay, so find out why it is taking place and why it is taking place there. Now we proceed further. Algorithmic strategies. An iteration of an algorithm typically starts from the current point and wants to reach a next point, okay, which is this. And the step delta xk is to be determined by the algorithm. Okay, so how should the algorithm proceed to get a good delta xk, which will get you an xk plus 1 that is better than xk, hopefully. Okay, So quite often, how to get a good delta xk, that question is answered by splitting it into two parts. One part is which way to move from xk and how far to move. Which way? Direction. How far? Step size. These are two questions to answer. If you answer these two questions, then you reach the next point. Okay. However, there is a hidden question behind them. Okay. That is question 0. Which of these questions should we address first? Should we decide the direction first, or should we decide the step size first? Okay. So that is a question 0. And depending upon in which order you answer this question, okay, that is in which order you answer these two questions, you get two algorithmic strategies. If you first decide the direction and then how far, that gives you the so-called line search strategy. If you first decide how much step size you are ready to take and then decide which way, then you get what is called as trust region strategy. What is the sense of these two? From the current point xk, first decide on a good direction to move in which you expect improvement. And then once you have decided on the direction, then your function constrained to move along that direction is actually a function of a single variable. How far in that direction? Okay. So you are then minimizing f along that line, actually ray. Okay, 0 to that way, not the behind. Okay. So this problem, that minimizing something along a line, is called a line search, searching the minimum along a line. Okay. So this is the line search strategy. After reaching there afresh you decide another good direction from there, which may not be the same direction as you found from here, and continue that process. On the other hand, trust region strategy works in another way. It says that around the current point, we develop a local model of the function, which is much simpler than the actual function, which is very nonlinear. We don't know how. Okay. So develop a local model of the function in this manner. Xk is already given. We are there. For given delta x, what is f of xk plus delta x? So it actually becomes a function of delta x. Okay. That is the local model. Now you minimize this local model function. This function you minimize. Forget about the original function for some time. In a small region around the current point in which the model can be trusted. If the region is small enough around xk, then whatever information you have about the function around xk, based on that, whatever model you have built, that model will be quite close to the actual function in that little region. Okay, so that region is a trust region. So in that trust region, you minimize this model function to determine delta xk, and then apply that step to go there. Around that point, you will build another local model there, and you will take another little trust region around that point and continue. Okay. So this is the trust region strategy. So both strategies are good. Most algorithms operate on line search strategy, some on trust region. There are some algorithms which can be implemented in any of the two strategies. Okay. So this is what we need to discuss at this point about optimization algorithms. And otherwise, the entire course is full of different kinds of such algorithms. And whatever algorithm we pick up on these issues, we will discuss them, we will evaluate them, we will experiment on them. Okay. So most optimization algorithms are iterative, defined recursively, and therefore, to begin with, typically we need seeding with some initial guess solutions. That doesn't mean that if you do not have a good guess, you cannot start them. Because if the algorithm has global convergence, which you will expect an algorithm to have, useful algorithm to have, then it will still work. Notion of global convergence and local convergence of an algorithm are complementary. They are answers to two different questions. Both of them are important: effective, efficient. Okay. And optimization algorithms are often implemented in one of the two strategies, line search or trust region. So in the next lecture, we will talk about the concept of convexity of domains and convexity of functions. Thank you.